Hey guys, Ms. Peterson here, and welcome to AP Chemistry Lecture 2-2, all about ionic solids. We're going to be talking about how ionic compounds form and some of their properties. So, how do ionic compounds form? Well, obviously, like everything in chemistry, it's all based on Coulomb's law and the fact that opposite charges attract and same charges repel. Coulomb's law. So it is the attraction between the positive cations and the negative anions. They become positive and negative when they steal those electrons, thus forming a bond. So the metals will typically form those cations and nonmetals will form ions. And again, this is due to their relatively large difference in electronegativity between metals and nonmetals. So if you're kind of looking at this image here and picturing what's actually going on, sodium has one valence electron that it wants to lose. Chlorine has 7 valence electrons and it wants to gain one. So when that happens, the sodium becomes positive and the chlorine becomes negative, and opposites attract, thus forming sodium chloride or table salt. Now, we can also model this using Lewis diagrams, which I feel like is often really easy since Lewis diagrams only show our valence electrons. So, for example, magnesium has 2 valence electrons, okay? It's in group 2. And then we got chlorine. Actually, I'm going to color code this. Magnesium is our metal with its 2 valence electrons. And then chlorine is our nonmetal with its 7 valence electrons. So what's going to go on when these guys are near? Chlorine's like, hey, I want that electron. Magnesium's cool. I have one to give you. But magnesium's still one more. And if you got 1 atom of chlorine around, you got more than 1 atom of chlorine around. Okay, you never have just 1 atom. There's always going to be plenty around. So maybe there's another chlorine atom hanging out over here. And it's like, hey, I'll take your other electron. Hey, come give it to here. And we will fill up my octet. And therefore, I am happy. When Mg loses those 2 electrons, it becomes that Mg2+. When chlorine gains one, it becomes that chlorine 1-. So you can see their ion formation there. And you can also see we needed 2 chlorine atoms for 1 magnesium, aka a charge of +2 is balanced out by 2 negative charges, making our formula MgCl2. Okay, let's do the same thing for sodium. We got sodium has 1 valence electron, and oxygen has 6. So that sodium is going to give its 1 electron here. And if there's 1 atom of sodium around, there's another sodium around. Okay, so our formula then, the Na loses that 1 electron and becomes Na+. The oxygen has gained 2, so it is an O2-. So you can think of that formula as Na2O. Okay, cool? Okay, cool. So what those are called, those chemical formulas are called formula units. And it's really the lowest whole number ratio, because in a, say, sample of sodium chloride table salts, you don't have any that are like just sodium chloride. Each little crystal of salt is a full cubic lattice that may have like 1,000,000 atoms of sodium, or 1,000,000,000, or 7, if it's like, you know, a teeny tiny little grain. Yeah, but what we need to be able to do is just determine its formula based on its charge. So we have potassium. Potassium has 1 valence electron. It's in group 1, so it forms that K+. Oxygen has 6 valence electrons, so it likes to gain 2 and become O2-. So when they get together, we need to balance out those charges. So the formula is K2O. Okay, and then if we're given a formula, copper chloride, well, chlorine is always Cl- because it has 7 valence electrons. Copper is a weird one, okay? Copper can have different charges. It's a transition metal in that middle part of the periodic table. So we have to use the formula to figure out the charge. Since we have 1 negative charges, I know that the charge on the copper must be a 3 positive. Now, when we have charges on transition metals, we represent them with Roman numerals. So the name of this compound would be copper 3 oxide. Oh, not oxide, chloride. Yep. CO3 2- is a polyatomic ion called carbonate. Na+ is a sodium ion. So this is sodium carbonate. And since carbonate has a 2- charge, we're going to need 2 sodiums for it. So the formula will be Na2CO3. Okay. And then ammonium nitride, okay, nitrogen, or nitride is a nitrogen ion. Okay, so ide means an ion of an element. Okay, whenever it's ide, that's what it's going to be. Okay, like chloride, oxide. Okay, that's what that means. So a nitride ion is a nitrogen ion. Nitrogen has 5 valence electrons because it's in group 15. So when it gains, it'll become an N3-. And then ammonium is one of our polyatomic ions. We'll be talking about our polyatomics more this unit, and we'll be giving you a list of about 10 that I recommend memorizing just because it makes it easier when you're reading chemistry. Though for the actual AP exam, they do not actually expect you to memorize any polyatomic ion formulas. Okay. Ammonium is NH4+. Oh, I don't know why I wrote it there. Write it in the formula where it goes. So when we do this formula, since we have 3 ammonium ions, what we'll want to do is put it in parentheses. NH4, and then we have 3 of them. Okay. Now, when we do these, it'll always be the cation name first and then the anion. So it's always cation and then anion equals the formula. If you were ever wondering about which element to put first. Okay, cool. Okay, cool. So what factors influence the strength of an ionic bond? Well, again, this all goes back to Coulomb's law. So this is Coulomb's law when we have 2 charges that attract each other at some distance. And if you have more charge, you have more force. Distance between nuclei. If you are closer, you have more force. Okay? Because you have a lower radius. And same for that crystal structure. A denser crystal structure will typically mean a stronger bond. And by more force, what I mean there is a stronger bond. Yep. So the quantitative measure of ionic bond strength is called lattice energy, which is the energy required to completely separate 1 mole of the solid ionic compound into its atoms in gaseous forms. Okay, so that is things like if we have this compound LiF, okay, that's LiF solid, its lattice energy would be the energy needed to take that LiF and split it into an Li gas atom and a fluorine gas atom. Now, obviously, fluorine is normally F2, so we'd have to break apart that fluorine. Lithium is normally a solid, so we'd have to get it to turn into a gas. And all of those steps are kind of part of the process if we were to calculate something like this. But if we're looking at this table to compare, we can see some of those trends, like magnesium chloride versus strontium chloride. Strontium chloride is 2 rows below magnesium on the periodic table, so it's a much bigger atom, so it has a lower lattice energy. Okay, if we're looking at this oxide series, okay, magnesium is the smallest atom bonded to oxygen, so it has the strongest energy. Yep. Okay, cool. So And that's what this is asking us to do. Compare the lattice energies, and how can we explain the lattice energy of the compounds formed between sodium and the halogens? So if we're looking for sodium and the halogens, that's going to be this series on the periodic table, where iodine, sodium iodide is the lowest lattice energy, and sodium fluoride is the strongest lattice energy. So why is that the case? Because fluorine's the smallest. Okay. You go down that group of halogens, from fluorine to iodine, the atomic radius, well, I guess in this term it would be the ionic radius, increases. So the bond is longer, okay? Farther distance, which means less force of attraction / lower lattice energies. Okay, all going back to atomic radius and Coulomb's law. Okay, let's see. If we're going to rank these from the weakest bond to the strongest bond, okay, we're going to need to consider the charges of these ions. So I'm going to go ahead and write those in real quick. Mg is Mg2 plus, nitrogen is N3 minus, calcium's a 2 plus, oxygen is a 2 minus. Okay, calcium 2 plus, nitrogen 3 minus, Mg is a 2 plus, and oxygen is a 2 minus. Okay, so some of these we can already tell immediately. The magnesium and the nitrogen have a stronger charge, so that's going to be a bigger bond. And then we have the calcium and the oxygen. So if we're comparing the calcium oxide to the magnesium oxide, okay, we know the magnesium oxide is going to be stronger. Okay, so we know that calcium oxide is going to be weaker than magnesium oxide, okay, because calcium's a bigger atom, so that bond is going to be bigger. Magnesium's a smaller atom, so those nuclei can get closer and form that stronger bond. And then let's go ahead and compare the magnesium and oxygen to the magnesium and nitrogen, since those have the magnesium ions in common. Well, the nitrogen has a stronger charge. Oxygen and nitrogen are right next to each other on the periodic table. So even though oxygen is slightly smaller, it's not going to be that much of a difference. So my guess is that that bigger charge of nitrogen is going to make it a stronger bond. So we'll say Mg3N2 will be that next one. And then again, calcium is a bigger one, so calcium's going to be weaker than that. But honestly, I don't think we can tell if that calcium would be here or if it would be here. That radius is squared, so that makes that a bigger factor than the charge, but the charge is like 50% more, so that is an impact. So I can't say for sure where that one would go. But we can definitely compare the ones that have things in common. Okay, we know that calcium will be more than the oxygen. I just don't know if it's going to be more or less than the magnesium oxide. And that's okay. Okay, last thing is the structure of ionic compounds. We call it a crystal lattice. And there's a lot of different types of crystal lattices. It could be what you're probably used to seeing with sodium chloride, where it's just every other, and it's all like in a cube with like one in the middle, and then there's 6 around it in the plane. But there are other structures, like this cesium structure, where the cesium is in the middle, and then you have the chlorines all around it. Or this face-centered cubist lattice with the zinc and the sulfur kind of bonding in that 1-to-1 form, but on a more diagonal. And again, you don't need to know or memorize any specific names of crystal lattices. Just know that they exist. And if there is a more densely packed crystal structure, that would be a stronger bond. So how does the structure help explain the brittle properties? We talked about this a little bit in our last lecture, but what you can kind of picture is, say I have all of these positive charges. Okay, this is going to be my sheet of metal, okay, or sheet of salt. Okay, it's an ionic. Nope, I didn't want to use green, I wanted to use red. Okay, so if we picture, okay, striking this with a hammer. Okay, there's my hammer, and I'm going to hit this. Okay, what could happen is it could cause this chunk to move downwards. Okay, and if that chunk moved downwards, let me see if I can actually show it like this. There we go. If that chunk were to move downwards, now, hopefully you guys can see we have negative by negative by negative and positive by positive. So those repel each other and break. It's brittle. If you got the two ions next to each other, they're like this, attracted to that same ion. You strike it with a hammer to get it like this, and all of a sudden it's like, negative charges next to negative charges, and it repels. And that's why salts and all ionic compounds are brittle. Okay, cool. That's it for ionic solids. Okay, cool. Okay, cool.